1, not 0.
Sorry.
The last number is 1 there.
Sorry, 1.
So it's pretty cool when you start playing around with these things, how it coincides.
Yeah, it's a beautiful thing. If you've ever, learned linear algebra and done this and worked out your matrices, it's such a drag. But to represent them in terms of Dirac notation, that beautiful rule, you just simply go through quickly and you can start Xing out most of it, and then you get a nice result in the end. One day, Peggy will have an appreciation for Dirac. Not there
today.
yet. Not today. I need to say one more thing. Before we actually finally get to a quantum search procedure, I need to say something. We had a specific operator called the Hadamard operator, which performs magic for us. So we usually
I love it.
It's like magic.
Can I have the Hadamard
Put
operator?
it in your pocket.
I know,
Walk
I need
around
it.
with
I need some magic.
H is for Houdini.
Actually, it was just his birthday a couple days ago.
That's right.
He would have been 137.
Oh, wow,
Don't
there you
ask
go.
why I know that. So the H gate, I'm just going to give it to you in the Dirac notation. I'm not going to give you a matrix representation. It's just saying that it takes 0 and it gives you this sum. It takes 1 and it gives you this sum. And so now the reason why I bring this up is because if we start off with our X register, usually we start off everything set to 0. And this is what we like to start with. So for the next algorithm anyway, we're going to start that way. So when I write this, I mean that we take our basis state here and we tensor it with itself n times. So this is usually our start. And now to get that beautiful superposition that I talked about earlier, what we do is we apply the Hadamard operator to it. And we get our beautiful superposition. What is it? 2 to the n minus 1, right? 2 to the n minus 1. And so that's why we need our Hadamard operator. It gives us a beautiful superposition, and then that's our starting off point. We proceed from there.
You get a scalar factor in the beginning? 1 over?
Yeah,
2.
1 over. Sorry, I'm being sloppy, right? 2 to the n. Thank you. Okay, so here's our quantum search procedure. So this is the beautiful procedure that we modified many, many times over in order to answer our group theoretic questions. So in '96, Grover gave this quantum search procedure. He wanted to search an unsorted list with n entries. And so he has the input and the output in this beautiful superposition of states. And having this, he's able to find the object on the order of root of n time, meaning that he performs root of n computational steps in order to determine the object that he's searching for. And so suppose we want to search through n elements, and we index them 0, 1 through n minus 1. And we're going to assume that n is a power of 2. So the index is stored in n qubits or n bits. And then we're also going to assume that the search problem has one solution. It also works if there are multiple solutions, but just for clarity, let's just assume we have one solution. And so in order for this to work, we need to have a function that recognizes the solution. So remember, we're searching through 0, 1 through n minus 1. And so for each element, we need to answer the question, is this the solution, yes or no? If we're not able to recognize solutions to the search, then this falls apart. It doesn't work. So let's define the function. It's 0 if it's not a solution, and it flags it. It spits out a 1 if it is a solution. And so now what we build up is what we call the oracle. So the oracle has the ability to recognize the solutions, and it relies on that function f of x that we mentioned earlier. And so The oracle is going to be an operator. We view it as a quantum logic gate, right? So it's going to be either it has matrix formulation or it could have a Dirac formulation. It's a unitary operator. It's defined on the computational basis, 0, 1. And so this is what the action looks like. And so what happens is the Q throughout the computation remains the same. And so because of that, we omit writing it. And this here means addition mod 2. And so for shorthand, this is what we write. Because the qubit Q remains the same, that's your oracle qubit, you just omit it. You don't even write it here. And so when the action of the oracle on your on an element from your computational basis, it gives you this. So it's going to flag it according to the result of f of x of that function. So here's the procedure. As I mentioned earlier, we start our n qubit register. Everything is set to 0, right? Just as before, everything is set to 0. Now we're going to apply our Hadamard operator. We're going to get our superposition just like this. And then once we have that nice superposition, we define what's called a Grover iteration or Grover operator. And this Grover operator is going to be applied finitely many times. And then once we apply this Q finitely many times, and notice I'm not telling you exactly how many. We'll talk a little bit about that in a moment. At the very end, we perform a measurement. And we have our solution. And so what happens is the following. Once we apply our Q, let's call this. Let's just give this a name. Once we apply our Q to this, remember how that oracle was flagging the solution, or solutions, depending. What happens is we have this giant sum. Now, if you look at each summand, you can look at what the coefficient of each summand is. And so when you apply Q, since the oracle is part of Q, it's going to be flagging as you go. So you may have a -1 thrown in here. I don't know, whatever this was, little n. Let's say it was for this one. And then we have the sum of the rest. So remember we said we had one solution in this case? Then that one solution is going to be flagged. Remember we had -1 to the f of x. F of x could be 0 or 1 depending on whether it's a solution. We're going to be able to flag it. So when you perform a measurement, you're going to look and you're going to say, hey, my coefficient of this one is different from the coefficient of the rest of them. I know that this must have been my solution. And so we have a way of representing this. This, what's above, is called, I don't know if you can see this. Let me roll. It's not a good picture. This is representing what's happening. We start out with our n qubits all set to the state 0. We apply our Hadamard operator. Now we have a uniform superposition. And our G, which is really my Q. You see it as G for Grover, or you could write it as Q. It's applied finitely many times, and then you perform a measurement at the end. And so now let's just talk how many times do we have to apply this Q or this G. So if there's a single solution, you're going to apply a root of n times, where n is the number of elements you were searching amongst. So it's not even polynomial, it's sub-polynomial. So it's a great algorithm. It's really quick. It's a lot better than any of the best-known classical algorithms for accomplishing the same thing. And so